Okay, so this is part 2 of our topic 10. So good day everyone. So we will be discussing more about or these are the next topics. So first, explain the principles and fundamentals of a refrigerator or refrigeration cycle. So we will discuss that uh, on our next. Okay, so this Carnot engine was already discussed um, on our previous topic, and I think it is topic topic 8. Okay, so wait. So refrigeration. Okay, so this is our refrigeration. Okay, so let's go back with our slide. Okay, so oops. Okay, so here. So this is our refrigeration cycle. So as you can see, so let's focus first on our uh, picture on the left. Let's just focus first here. First, we have a compressor. So this is a refrigeration system. So the four basic components of the refrigeration system, we have the compressor, the condenser, the expansion valve, and the evaporator. Okay, or expansion valve, or TXV, thermostatic expansion valve, TXV. Okay, so let's start with the compressor. So the compressor, the function of the compressor is to compress the refrigeration, the freon or the refrigerant. Okay, so refrigerant, we have two types, two phases for our refrigerant. We have the liquid phase and the gas phase. So in the compressor, it is, since liquid is incompressible, is not compressible, then we should then the compressor only compresses a gas type of our gas phase of our refrigerant, the gaseous phase, PHASE. Okay, so compressor. So the compressor compresses the gas refrigerant. So as the gas refrigerant is compressed, so the temperature of it increases, and and that's all, the pressure is also high. So high pressure and high temperature. And then as it goes to the condenser, so the condenser will absorb the heat from the compressed refrigerant. So heat is removed outside. So for example, if this is air conditioning, so heat is removed outside of the room, right? So as you can see, there are refrigeration aircon system like a split type. So outside the room, you can see a blower, and then that blower will be kind of a warm or hot air is going in that blower. So that is the condenser outside the room. Okay, so in the condenser, the compressed refrigerant, hot, com hot the compressed refrigerant, which is hot, so its temperature is uh, cooled cooled down by the condenser. So the heat is removed by a blower, and then as the refrigerant goes outside the condenser, so the temperature um, of the refrigerant is goes down, and then from gas it turns to liquid, right? Turns to liquid. Then after that, the liquid refrigerant is cooled down, and then it has still a high pressure, but the temperature is low. So high pressure, low temperature. Okay, so as that high pressure liquid refrigerant goes outside the expansion valve, so expansion valve, the use of the expansion valve is so that the refrigerant going outside this valve will expand. So if it expands, the liquid refrigerant, if the liquid refrigerant expands, so some of it turns into gas, but most of it is still liquid. So there is the combination of gas and liquid refrigerant going out from the expansion valve. And then after that, the evaporator, after that, the refrigerant will go to the evaporator, cooling down the evaporator, and then if air is drawn into the evaporator, so the hot air from the room, for example, is drawn into the evaporator, so it cools down, and then after that, the air is blown into back to the room, so that the cold air will be felt in the room, while the hot air in the room is the hotness of the air in the room is absorbed by the evaporator, in which the refrigerant will absorb the heat from that hot air, and then that hot air is turned to cold, and then the refrigerant will the cool refrigerant will be increasing its temperature. Okay, so that liquid refrigerant, turns into high pressure and high temperature gas, or low pressure but high temperature gas refrigerant, and then it goes back to the compressor to be compressed, turning it to high pressure, high temperature, and then the cycle goes on. So as you can see, here we have a PV diagram. Okay, so as you can see, first let's go from the compressor. So compressor from 1, so here's the 1. Okay, so from 1, if you put the refrigerant into the compressor, you compress it, so you increase its pressure, right? So increasing its pressure, so this is the curve. So this is adiabatic. So the curve for compression, 1, 2, 4. Okay, then after that, the high temperature and high pressure refrigerant, so as it goes to the condenser, so it is cooled down, or the heat is removed from the refrigerant, so the volume of the refrigerant decreases, going back to liquid while maintaining the pressure. And then after that, in the expansion valve, the refrigerant will expand, decreasing its pressure, and then also increasing its volume, since it is expanding. And then after that, it goes to the evaporator to absorb the heat from the room, or from the evaporator. So the refrigerant will increase its temperature, thereby expanding to gas, but the pressure is still the same. So this is how it works. And then after that, it goes back to the compressor, compressed, increasing its pressure, decreasing its volume, and then that's the cycle of the refrigeration cycle. Okay, so that is refrigeration cycle. So this is an example of a refrigeration cycle. So as you can see, there is a kind of this curve, this broken line curve. So in this curve, as you can see, on this side, the left side of the curve, we have liquid. Inside the curve is liquid vapor, while outside the curve is vapor. So this curve signifies whether the phase of the refrigerant. So it is like liquid in this side, and then in this side liquid plus vapor, and this side it is mostly vapor. Okay, and then okay, so next we have the Carnot cycle, but this cycle was already discussed on our previous topic, so we will not be lingering much time on this topic. So this was already discussed on topic, I think it's topic 8, so you can just look over there for the information for Carnot cycle. Next, we will go for the Rankine cycle. So Rankine cycle is usually used on boilers or steam engines. So as you can see here, okay, let's see, there is fire in the picture. So this one, so this fire, this is the one that will be boiling our water into this coil, heating coil. Okay, so this is the boiler. So this is a boiler. In the boiler, we increase the temperature of our water, thereby increasing also its changing its phase into steam, from liquid to steam. And then as the steam pressure goes up, and then it becomes dry. So that dry steam will be the one that will be pushing the blades of the turbine to rotate. So the turbine will rotate, creating work. So you can put a generator in the side, or you can connect it to a propeller or something that will be used as work for the turbine. And then as the steam pressure lowers down, since the energy of the steam is already used by the turbine, it goes here into the condenser, and then in the condenser, the hot steam will be cooled down by a cooling liquid, either seawater or fresh water. So the steam will be cooled down, turning it back into water, and then that water will be pumped or sucked by the pump and pushing it back or moving it towards the boiler again. So that is the complete cycle of the Rankine cycle. So let's try to check in the diagram. This is a TS diagram, or temperature entropy diagram. Okay. So as you can see in the diagram, from 1 to 2, so that is the time where you suck the water from the condenser. So water is sucked by the pump and then pushing it into the boiler. So since the boiler is kind of hot in there, so the temperature is slightly increasing as the water enters the boiler. And then in the boiler, when the water is already in the boiler, so the liquid, so you increase its, as you can see, from 2 to 3. That is 2 to 3. Okay, from 2, temperature is increasing until it is still in liquid phase. So the temperature increases, and then slowly turning it into a steam. So in this case, it is wet steam. So it is like a liquid with vapor. So it is wet steam, and that it goes to number 3, it is turned into dry steam. So that dry steam will be the one that will push the turbine to rotate. And then as the pressure decreases, so 3 to 4, the pressure or the temperature of the steam decreases, but it is still steam, but the temperature decreases. And then as it decreases, so work is created while temperature is decreasing, because the heat of the steam was consumed by the turbine. And then after that, 3 to 4, so from 4 to 1, so what steam was cooled down, so it is converting back into liquid, thereby decreasing its entropy, since the molecules of the steam is much there are more movement, so it has high entropy. But if it is converted into liquid, so the entropy of the steam to liquid, the entropy decreases. So that is 4 to 1. And then back to the pump for suction, and then the cycle goes on. So that is for the Rankine cycle. Okay, next. So this is steam turbine. So if steam is, as you can see in the picture, there are blades or tooth or blades. So those blades are kind of angled, so that if steam enters into the blade or goes into the blade, so there will be a rotational motion of the turbine. Okay, so this is an example of a steam turbine. So in the bottom, we have a picture. So in the bottom picture, we have a steam turbine which is connected to a generator. So as the turbine rotates, so the generator will also rotate, thereby producing electricity. Okay, next we will be discussing about Brayton cycle. So Brayton cycle is more on gas turbines. Okay, so let's see the PV diagram. So first we will go the picture here. Okay, so in the Brayton cycle, we have a gas turbine. So in the gas turbine, this is the picture, or the kind. This is what gas turbine is. So how it works? So first, this is the compressor side. In the compressor side, so air is drawn and then compressed by the turbine blades. So this in this stage, since the turbine cannot rotate on its own, so we can put a motor or something that will rotate the turbine on this phase, so while it is still starting. Okay, so air is drawn into the compressor and then it is compressed. So as the air is compressed, temperature increases. And after that, fuel is injected into that compressed air, thereby producing a combustion, since hot air with fuel creates combustion. So that combustion will create high pressure move, thereby increasing the speed of rotation of the turbine. So since this is all connected into one shaft, so as the combustion moves in here, so the turbine will increase its speed, thereby it will turn on itself even without the rotation of the motor or something that drives it. So the combustion itself will drive the turbine, increasing its speed and increasing its efficiency until the gas goes outside, goes here on this side, but the turbine is already in its maximum rotation. So thereby work is already made. So if you are putting a synchronous motor on this turbine, so maybe during starting you use the motor to drive the turbine, to rotate the turbine, and then when it already creates its own combustion, so it doesn't really need the motor anymore. So if the turbine rotates, then that motor can be turned into a generator, thereby creating electricity. You can also use that. So that is a synchronous motor. Or maybe you can use this as a you use this in on our airplanes, or to increase its speed, so the airplane can fly. You can also use that. Okay, so how does this work? So what is the cycle PV diagram? So first, fresh air is drawn into the compressor since the compressor is rotating, and then after that, when the air is already compressed with high pressure and high temperature, you inject fuel and then combustion occurs, thereby turning the turbine, or forcing turning the turbine faster than and since it has one shaft, so the compressor will also increase its speed, so the cycle will make its own. So the gas turbine will rotate on its own already, and then exhaust goes to the atmosphere, and then in the atmosphere you get fresh air again for the compressor, so the cycle goes on. And then if you plot it on a PV diagram, so from fresh air here, atmospheric pressure higher than zero, atmospheric pressure, as the air is compressed, so pressure increases while volume decreases. So that's what this curve is all about. And then 2 to 3, that is where fuel is injected and combustion occurs. So the gas will expand, so volume increases, expand, and then those expansion will turn the turbine, that is 3 to 4, turn the turbine more to rotate it more, thereby decreasing so the turbine will rotate, the pressure will decrease while the volume continues to increase, expand outside the turbine. And then you remove the hot gases, exhaust gases, and then you remove hot gases, so the cycle will go back to 1, so back to atmospheric pressure, fresh air. Okay, so that is for the Brighton cycle. So that is the PV diagram for the Brighton cycle. Okay, next, explain the parameters of pH diagram and PV diagram of a refrigeration cycle. So we already discussed about the PV diagram for the refrigeration cycle. Okay, explain the purpose and the parameters of a molecular diagram. So in the molecular diagram, we have a liquid on this side, we have liquid and steam on this side, or liquid or vapor, and on this side we have vapor. Okay, so a molecular diagram is useful because it allows us to visualize and compare different refrigeration and heating cycles. So you can compare a brand new engine, and then for example, if you go to a 5-year-old ship, for example, and then you want to check whether your refrigeration is still on its optimum value, so you can use the molecular diagram, and then you can compare your current molecular diagram from the diagram when it first came into your ship. So you can compare the new and your current readings, and then after that you can check whether your uh, uh, refrigeration, for example, is at its maximum performance or optimized. So you can check if there are problems, you can optimize your equipment if there are something to be improved. Okay, so using that molecular diagram, so it is useful because it allows us to visualize and compare different refrigeration and heating cycles and optimize the performance of the equipment itself. So that's the use of the molecular diagram. Okay, next we have calculations. So for calculations, work is equals to Q in minus Q out, or Q of the heat of Q hot body minus Q cold body. Why? By the way, Q is heat. Okay, while efficiency is of a internal combustion engine is equals to work over Q in. Okay, so we have a problem. So QH, or hot reservoir, is 850 joules and QC is 375 joules. So what is the efficiency of this combustion engine? So we can use the formula efficiency is equals to work over QH, and since work is equals to QH minus QC, so we can also use that. Work is equals to QH minus QC equals 850 joules minus 375 joules. So the answer is 475 joules, and then divide it by QH, which is 850 joules. So our efficiency of our engine is 55.88%. So you can use the formula, these formulas. So we have some other problems and exercises. You can use those formulas to answer these problems. Okay. Next, for Carnot engine. So for formula for the refrigeration, so we have COP equals QC over work, heat of the cold body over work, and work is equals to QH minus QC. But for the Carnot engine, this is the formula. Efficiency of the Carnot is equals to 1 minus temperature of the cold, lowest temperature, over the temperature of the hot with the highest temperature in Kelvin. Okay. So that's for efficiency. So for number 1, for example, a certain gasoline engine has an efficiency of 30%. So what would the hot reservoir temperature be for a Carnot engine having that efficiency if it operates with a cold reservoir temperature of 200 degrees Celsius? So first to do is convert 200 degrees Celsius to Kelvin. So 200 plus 273. So that is the 473 Kelvin. And then using that formula, we can transpose, or we can use that in our formula. So our formula is, we go back, is efficiency of the Carnot equals 1 minus T cold over T hot. So since T cold, our value for T cold is 473 Kelvin. So we will have to transpose the values. So first is efficiency, which is 30%, equals 1 minus 473 Kelvin over T hat. So first is transpose efficiency, Carnot efficiency 30%, 0.30, move it to the right side of the equation. So you will be converting it to -1 minus -30, while the T cold over T hat will be transposed on the left side of the solution. So it will be turned into positive T cold over T hat, and then cross multiply T hat will go up, while 1 minus efficiency of the current goes down the T cold. So T hat is equals to T cold over efficiency of the Carnot 1 minus 0.30. So T hat is equals to 473 divided by 1 minus 0.30. So the answer for that will be the answer for number 1. So we have also sample problems 2, 3, 4, 5, 6, 7, 8, 9 if you want to practice. Okay. Next, for the Rankine cycle, the formula for the Rankine cycle, we have here the formulas. Okay, this is for the boiler or the steam engine, so Rankine cycle. So these are the formulas. So this one will be, we will be using the first work of thermal efficiency, or equals to work of the turbine minus work of the pump over Q in. So we will use this formula. And later on your auxiliary machinery subject, for Mollier diagram, you will use the other formulas on your second year, when you will be second year. Okay. So we have a problem number 1. So in a simple Rankine cycle, the work output for the turbine is 80,000 kilojoules. The work input to the pump is 2,000 kilojoules, and the heat input to the boiler is 200,000 kilojoules. Calculate the thermal efficiency of the Rankine cycle. So the formula will be this one. So thermal efficiency equals to work of the turbine minus work of the pump over QH. So the value for the work of the turbine is 80,000 minus the work of the pump, which is 20,000, divided by QH, which, or the input to the heat input to the boiler, which is 200,000. So using the calculator, your answer will be the answer for number 1. And then we have problems 2 to 3 if you want to practice this formula above. Okay. Lastly, we have calculating parameters for a gas turbine. So the formulas for gas turbine will be this one. So on the bottom, thermal efficiency equals to net work over heat input, which is equals to work of the turbine minus work of the compressor over Q in. And then we have other values, other formulas. So these formulas will be used on maybe on your third year on your past GT subject, which is more on gas turbine. So we'll be using the second formula, the work of the turbine minus work of the compressor over Q in, for the meantime. Okay, so problem number 1, a gas turbine produces 80,000 kilojoules of work output from the turbine, 20,000 kilojoules of work input to the compressor, and has a heat input of 150,000 kilojoules. So calculate the efficiency. So as you can see, the formula will be efficiency equals work of the turbine minus work of the compressor over Q in. So the work of the turbine is 80,000 kilojoules minus 20,000 kilojoules, which is the work of the compressor, divided by 150,000 kilojoules, which is the heat input. Okay, so the answer for that one will be your answer for number 1. And then we have problems 2 to 3 if you want to practice more about these formulas. So that's it. So that's it for this video. I hope you have learned many things, and please do subscribe and share our video. Thank you so much for watching, and God bless everyone. See you on our next video. Bye bye.